For those of you joining us on the recording, hello, welcome, welcome. Thanks for watching. A couple big areas that I foresee some students having some issues on is naming, right? Naming has been a large portion of this entire unit, and I want to make sure that we can all use it and do it. Now, with naming, there are two different flavors. You've got your ionic. Your ionic. And you've got your covalent. Let's start off with ionic. Ionic bonds are between a metal and a nonmetal. If you want to get more specific, it's between a cation and an anion. So a couple good examples of this would be your salt, NaCl, FeCl2, NaS2. What else? You've got your BeBr. Right, all of these are different styles, right, of just the same thing, different flavors of the same thing. Now, how can we name these is the big question. It's a reasonable question, right? You take just the metal, put it together with the nonmetal, and add your IDE at the end of your nonmetal. Now, ooh, what does that mean? Take Na2S. Na is sodium. So just the word sodium. And this one here is sulfur. Now, we change the ending of sulfur to IDE. So sodium sulfide. That's it. There's no funny business here, right? It's, chemistry tries to be as confusing as possible, but the reality of the situation is we're trying to make it as easy as possible. Let's do another one. Let's try MgCl2. All right, take a second. This first one, Mg, is magnesium. Now we don't add anything, we don't take away anything, it's just magnesium. Then chlor comes from chlorine, and then the IDE at the end. Questions are now starting to come in. Good. The question, let's talk about this first question here. Where does the 2 go? So this 2 that's here is what I'm assuming you're referring to. And this 2 here is what I'm assuming that you're referring to. It doesn't go anywhere. With ionic naming, all subscripts are implied. That's why you don't need no mana, die, try, ... Now, what we mean by that additionally, right, is that if I give you a name of, say, I don't know, sodium, and let's say sodium nitride, right? Now we just work in reverse. All right, what's sodium? Sodium is Na with a 1+ charge. And we know it's a 1+ charge from its location on the periodic table. We additionally know that nitride is nitrogen, and nitrogen has a 3- charge. We know that again from its position on the periodic table. From here, we do our criss, 1 cross. Or we take this subscript here, and all we do is we put that 1 down here. We take this 3, and all we do, we put it down there. That's it. You get rid of any other junk you have on the top, and you're good to go. We can clean this up just a little bit by writing it as Na3N, right? Because that 1 is implied. So a good question that you could see on an exam would be, how can we, given the name of sodium nitride, what's the formula? Given a formula of, Na2S, what's the name? We're not trying to do anything tricky here, but that's how it would be posed as a question. Now, occasionally, we have problem children. We'll use red. What if we've got something along these lines? PbNO3 2. Go ahead, for the people in the call, go ahead and take a second. Try figuring this one out on yourself. How would you name this one? Grab a quick drink of coffee, and then we'll get started back again. If you said lead nitrate, you would be halfway there. The reason why you're halfway there is because of this problem child, the Pb. The reason why is because it can have multiple charges, right? Lead can have +1, 2, 3, all the way up to 4. Iron can have 1, 2, 3. Manganese can have 1, 2, 3, 4, 5, 6. And maybe thinking to yourself, whoa, Mr. Boozray, am I going to need to know all these? I can barely remember what we had for breakfast this morning. No. Instead, we can use clues to figure it out. Watch carefully. Now, recall, I don't know the charge of PB, right? I don't know the charge of PB. Right, off the top of my head, don't know. Let's call it X. All right. Now there is a charge we do know. That charge, NO3. On your periodic tables. Right, we know this charge of NO3 to be 1 minus. We do know the charge of NO3. This charge is 1 minus. And we get this from the periodic table that you'll get on the day of the exam. Now, a key thing that I see a lot of students mess up here is how many. We now need to count how many. So how many leads do I have? There's no number, it's 1. So I've got a 1x, and I need to add that together. And I need to add that together with 1 minus. Now, how many 1 minuses do I have? You guessed it, 2. So I put 2 here. The big thing that needs to be here, though, is that this all equals 0. Now, just solve for x. When you solve for x, x is going to equal 2. Now, this 2 is the charge of PB. Now, heading back up here, the important reason why we needed this is because we need to denote what charge this lead has that we're working with. If we don't know what charge it has, then we could say it's at PbNO3 instead of PbNO3 So we showcase this by using Roman numerals. Lead to nitrate. Now, a good question on the exam, because we've actually been seeing a lot of students be getting some really good results with this stuff down here, would be consider this compound. Right, consider a compound of MnSO4. Right, consider that compound. A good question would be, what charge the manganese have? Now, for those of you in the call, go ahead and take a second, try figuring it out. Right, again, we need to use the X as our charge for Mn. We've got 1 Mn. Then you need to look on the periodic table for your charge of your sulfate, which is SO4. So again, let's call Mn's charge. Right, let's call Mn's charge, I don't know. Let's call it X. Now, I've got one X here because there's no number by the Mn, plus the quantity 2 minus. And now how many sulfates do I have? 1. All equals 0. So that means X is equal to 2 plus, where the charge on Mn is 2 plus. Now, before we get into covalent compounds, there's a question in the questions chat that I'd like to address first. Again, for those of you who joined us late and you may be asking yourself, how can I ask a question? Locate on the bottom right-hand side of your screen, you should see a triangle, square, and a circle, all kind of in one little area. If you click on it, you should see Q&A. Let's talk about VSEPR really quick. VSEPR, which stands for valence shell electron pair repulsion. All right, so valence shell electron pair repulsion. It's a theory, right? It tells us kind of where we can find our atoms when we're looking at it on a 3D plane. Now, you don't need to remember what VSEPR stands for the exam, but for the final exam, it might be a good thing to keep in the back of your mind. Now, there are 6 different flavors of VSEPR for the exam that I'd like you to be aware of. Now, on this chart, I'm going to have name, the number of lone pairs on the central atom, bonded atoms on the central atom, and then the shape. Let's talk first about linear. Kind of just like in math, linear is a line. 0 to 2 lone pairs, or sorry, apologies, not 0 to 2 lone pairs. 0 lone pairs on the central atom, 0 to 2 bonded atoms on that central atom. So an example would be, right, if we have oxygen and oxygen. Right, just nice flat. Another good example, we've got C with the O next to it. If we locate here at the bottom of the C, there's no lone pairs. Neither up here, no lone pairs. So there are no lone pairs on this carbon. Next one. You've got bent. Now there are actually kind of 2 flavors of bent. So remember how linear had no lone pairs? What if instead we had one lone pair on that central atom? What about 2? 1 or 2 lone pairs on that central atom. Now, for this, you do need 2 bonded atoms to that central atom. Observe. So if linear is just a line, take a second to think, what would bent be? If you said looks like a bent shape, you'd be correct. Good example of this is water, H2O, like this. Another good example of this is SO2. Look carefully. On water, there are two sets of lone pairs on that central atom. Now that's what makes it bent. On sulfur dioxide, there are two sets of apologies, there is one set of electron pairs on there. Will there ever be lone electrons that are not paired? No. Right, electrons don't like to be all alone and all lonely. All right, so 3 down, a couple more to go. All right, let's up the ante a little bit. We've done 0 and 2 bonded atoms. What if this time we have 3 bonded atoms? Okay. Let's not be crazy right now. 0 lone pairs. Okay. Nothing crazy. No lone pairs on that central atom, right? All of this, both of these columns are talking about stuff that's on that central atom. This would be called a trigonal planar. Now, a great way to how to remember this, when you're out driving, especially when you're going up north, everything's flat because you're going through the plains, a flat plane. So if something is trigonal planar, what do you think its 3D geometry will look like? If you said flat, you'd be absolutely correct. Watch carefully. We've got B. Let's say we've got 3 F's around it. And we're going to make it a little bigger. Bam. Wabam. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Notice here, on this boron, no lone pairs, 3 bonded atoms. Trigonal planar. All right, let's go crazy. 3 bonded atoms, 1 lone pair. I know, we're crazy now. Oh, just imagine. This would be a trigonal pyramidal. Now, take a second, put your thinking caps on. If trigonal planar was a flat surface looking like a plane, what would pyramidal look like? You said it looks like a pyramid? Gold star. Matt, give yourself a little pat on the back, right? You're doing good. Observe. So here, on this ammonia atom, I've got 1 lone pair, right? Again, pair means 2, so 2 electrons, and 3 bonded atoms. Let's do one more. We're feeling it. We're feeling it. Let's do one more. Let's not get too crazy. 0 lone pairs on that central atom. 4 bonded atoms. Observe. methane. So again, notice here, right? 1, 2, 3, 4 bonded atoms. 0 lone pairs on the central atom. For the person who pointed out my mistake up here, you are correct. The mistake up here was that this oxygen had too many electrons. It should only have 2. Or 2 pairs, I should say. Now, you may be saying, well, Mr. Boost, right? You know, this is a funny shape, right? We'll call back to your covalent naming. Tetrahedral. Tetra meaning 4. 4 atoms. Tetrahedral. A great example of a question using this chart would be, all right, consider you have this compound. Let's say you have the compound O3. Say you got that compound. What is the molecular shape? All right. Whenever you're determining molecular shape, your first step always needs to be count valence electrons. Always. That's your first step. Because if you don't count your valence electrons, you could end up with a structure that looks stable to the naked eye, but we can't gain or lose any valence electrons in this case. It's not like in ionic bonds where everything is just being transferred. Here, everything's shared. I can't lose anything. Three times 6, I get 6 from the periodic table. Because oxygen has 6 valence electrons, so this would equal 18 valence electrons. Your second step is to try a structure. Now, remember your octet rule. And remember that it must have your number of valence electrons. It must, no matter what. Observe. Let's say, and I'm going to do this in red because this is going to be bad. Let's say, all right, I got oxygen. Let's try 2 single bonds, right? All right. I look at my first oxygen, the oxygen on the left. How many valence electrons does it now need to be stable? If I get 2 from that line, 8 minus 2 is 6. Needs 6 valence electrons. 1 at the top. Got 2 lines. So it means I need 2 pairs. Oh, I'm going to make that one look a little nicer. All right, 1 on the right. All right, let's try it again. All right, now that everything's all stable, your last step, step 3, is count. Number of electrons. You can't have more than what you started with. In this case, I cannot have more or less than 18. You must have what you started with. If you don't, Doesn't work. Observe. Let's count this together. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Here, 20 does not equal 18, meaning that this structure would not work. Let's try a different style. Let's try 2 double. All right, so that means that it looks something like this. Start with the oxygen on the left. How many more valence electrons does it need to be stable? Take a second. Think about it on your own. I'm all out of coffee in this cup. But a good man comes prepared. All right, if you said 4 more electrons to be stable to fulfill the octet rule, you'd be correct. 1, 2, 3, 4. 1 in the center. 0. Reason being, 2, 4, 6, 8. 1 on the right. You guessed it, 4 more. Count it up. 2, 4, 6, 8, 10, 12, 14, 16. Does 16? Oh, Jesus. Does 16 equal 18? No. It gets a sad face. Now, there's a good question here, right? There's 2 good questions, right? Does guessing and checking molecular shape always work? Yes. It takes a little more time, but I'd rather a method that works all the time and takes a little longer than a method that only works some of the time. You may be asking, how do I know where to place the valence electrons? I assume that means like when I'm placing here and here. We'll change it to green. Here and here rather than like here and here. This is just a stylistic choice, right? As long as you've got 4 extra valence electrons on here, you're good to go. So if a single didn't work, 2 singles, 2 doubles didn't work, what else could work? Aha, a single and a double. Great question. Let's try 1 single and 1 double. All right. This one needs 6 more electrons in order to be stable. This one needs 2. This one needs 4. Count it up. 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 is equal to 18 valence electrons. Now you reference your chart. What structure has 2 bonded atoms and 1 lone pair on the central atom? If you said bent, you would be correct. And that's exactly how this type of question will be structured on the test, right? You'll need to name the structure and draw the Lewis dot diagram. And guess what? That question A is, how many valence electrons does it have? Draw a stable Lewis dot diagram. What molecular structure does it have? Right? It's done in the order that we just taught you. I want to head back over here to answer a couple of questions that we had come up during our little intro with Vesper. For this one, why did we put 2 plus, or I guess we're assuming here, why did we put 2 plus instead of the Roman numeral 2? Good question. We only use Roman numerals when we're naming, not when we're looking at the charge itself. With the charge itself, we look at it just with standard Latin numbers. For the Roman numerals, we use those in naming. This 4 after the SO4, this one here, tells us absolutely nothing. It doesn't really affect our naming anything. All this affects is what this anion is. This was, say, instead of 3, it would change the whole thing, right? It would change from SO4 to SO3 is going from sulfate to sulfite. All this 4 means is what does this anion mean? Can we do another practice problem with Roman numerals? Absolutely. Let's say I give you this. Bum ba da dum. Cobalt 4 cobalt 4 chloride. While you're attempting that problem, I'm going to hit a question that about the, naming another Roman numerals, but what does electronegativity tell us? Electronegativity tells us the affinity for electrons. So how often is it to take electrons from everything else? The best way how I consider this is, right, if you're kind of electrons want to have a nice, complete valence shell. The closer that valence shell is to the nucleus, the more they want electrons. Now, we see a general upward trend, right? We see a trend that goes from the bottom left to the top right. And in fact, on the backside of every periodic table, I thought I had one here. The backside of every periodic table, it tells you that electronegativity. Again, all electronegativity is just the affinity for electrons. Will you have the complete 80 minutes? I believe we decided on 60 minutes. You got 60 minutes to do 8 problems. Let's go back to the cobalt 4 chloride. So we have CO. This 4 means, guess what? Has a charge of +4. Chloride, Cl, has a charge of 1-. You do your crisscross, CO, Cl, 4. That's it. No funny business, no nothing, right? Let's do another one. Let's try going from reverse, right? If I give you a formula, what's the name? Cu2SO3. When you're drawing a Lewis dot diagram on the exam, should you draw it in the correct shape even if it doesn't ask? Yes. If you're going to be drawing it bent, you should be drawing it bent. Absolutely. Take another second, finish up this problem. Again, your big thing here is you need to identify what charge does that copper have. Coffee break? Yeah, for those of you in Mr. Boos's class, your grades are up to date. Yeah, nice going into the exam. I'm also going to be posting the quizzes is if you're in my period 5 or period 4 that we did today. For period 5, we'll be doing it again tomorrow. All right. Combing my brain. Do I know the charge of copper off the top of my head? No. So that means I need to use, well, algebra. Let's call the charge of copper X. Now, question. How many X's do I have? I'll give you a hint. There's a red dot flashing next to it right now. 2. 2x. Now, question. What charge does SO3 have? You look on the back side of your periodic table. You see SO3 has a charge of 2 minus. How many 2 minuses do I have? The correct answer is 1. Why? This 3 here is stuck on that oxygen. It's only on that oxygen. It's not on the entire SO3. If instead it was something like this, now we would have 2. But because we don't, it's just like that, 1. Solve for X. So that means that this name would be copper 1 sulfite. Does a stable Lewis dot diagram always have 8 valence electrons unless the 3 exceptions? In general, yes. For this exam, yes. We'll do one more of these of just naming an ionic compound, and then I'd like to do the one where it's asking us to do everything. Draw the Lewis dot diagram, draw the shape, everything like that. Let's do this one. Zinc chlorate. Now, question. Zinc is on the periodic table, and it is in that transition metals. Why don't we have anything here? No parentheses, no nothing. The correct answer is because we know the charge of zinc. Take a second, look at your periodic table, identify the charge of zinc. If you said zinc had a charge of 2 plus, you'd be absolutely correct. Now on the periodic table, right, you got a little staircase, little action going on with silver being +1, zinc and cadmium being +2, aluminum and gallium being +3, right? Those are just unfortunately ones that you just kind of have to know. Chlorate, ClO4. One minus. Did you crisscross? Zn parentheses ClO4 2. Will we have to know the specific charges like zinc for the test? Yes. Even if you knew the charge, could you solve for it algebraically if you forgot the charge? Yes. Is it's yellow 3? If it's yellow 3, I apologize. It's still the same thing. Still gets me the same answer. Thank you. All right, let's do a big example. Let's do a big example. Let's say you're given the compound, we'll use green, CCl4. I want to know the following. Lewis dot diagram. I want to know the shape and the bond polarity. Go. Take a minute. Solve it. Burn my tongue. I can do a little motivational dance if you want. Get motivated, get motivated, get motivated, get motivated. All right, let's go through it. Will we need to know bond angles? No. Let's go through it. Now, all right. Carbon has 4 valence electrons. Chlorine has 7 valence electrons. And I've got 4 of them, so 7 times 4. So, of course, got your 28. Now, 4 plus 28, 32 valence electrons to work with. Quite a lot. All right, let's try to figure this out. Let's all do single bonds. All right, let's start with the chlorine at the bottom. How many valence electrons does it now need to be stable? Take a second, identify it. If you said 6 valence electrons, you'd be darn right. One, two, three, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And a 1, 2, 3, 4, 5, 6. All right, count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 10, 32. All right, so that would be a stable Lewis dot diagram. Now, the shape. 4 lone, I got 4 bonded atoms, 0 lone pairs. Tetrahedral. Now, Now we need to go over bond polarity and one last thing, the molecular polarity. All right, let's do it. Let's talk about bond polarity first, right? This is when you do the subtraction. All right, bond polarity. Bond polarity, right, you do your subtraction. Consider this. I've got the periodic table pulled up on my other screen right here. We've got chlorine, Cl, with an electronegativity of 3.0, and carbon with 2.5. 3.0 minus 2.5 is 0.5, which means that the bond polarity is polar. The bond polarity is polar. Keyword there. Now we get into a little bit more of a tricky situation. Let's first start off by drawing these dipoles, right? If I have these two dipoles here, right? If we've got Cl, Cl, Cl. Now, as a reminder, dipoles is just the direction that my electrons are going. Now, the dipoles, if they come in together, can cancel out. If they go apart, they can cancel out. That's how something that is nonpolar as a bond, or sorry, polar as a bond can be nonpolar as a molecule. The other way, the better way to figure it out, though, the best way to figure it out, look at your diagram. Where are your charges? Is everything symmetrical? Is everything nice, evenly distributed, or is it unevenly distributed? Here, I've got a nice even distribution of my valence electrons. That's why this molecular polarity is in fact non-polar. Yes, there will be questions regarding this. For dipoles canceling out, it's a little bit of a abstract topic. I don't really have too much time to go over it here. For now, though, focus on this, right? The fact that all of this, I say all of this by motioning at it, right? All of this, everything's symmetrical. Everything's nice, even. Even being the key word there. It is nonpolar because it is an even distribution of my electrons. Nothing's hoarding it. A good example of an uneven thing would be, SO would be H2O. Observe. Observe here. With this, is everything nice and evenly distributed? No. Look here at my oxygen. It's hoarding all of my electrons. I've got 8 around it and the other guy's got 2. Is that fair? Is that even? No, it's not. That's why it doesn't work. That's why if it's an uneven distribution of electrons, it is polar. If it's an even distribution of electrons, it is non-polar. The last question that I'd like to go, there's 2 more questions in here. When you're naming ionic bonds, you use Roman numerals when you don't know the charge, and you know prefixes for the amount of atoms in a covalent bond, correct? Going back up here, for covalent, it's between a non-metal and a non-metal, and uses prefixes. It is also 9 o'clock, so any questions submitted at 9 o'clock or past will not be answered, because I also want to get to bed at some point. But feel free to send me an email. We can follow up on it. Or come to the session tomorrow morning. I'm happy to answer them. The last question that I'm going to hit today is chemical reactions. 5 types that you need to be aware of and account for. For my chemical reactions. Five types. Start off with the easiest one, synthesis. A plus B yields AB. 2 things become 1. 3 things become 1. Right? All these things, right? Stuff that's starting apart comes together. So if synthesis is 2 things coming up together, what do you recommend? What do you reckon decomposition would be? 2 things coming apart. Oh. Single replacement. 1 thing is getting kicked out. That's it. Right? 1 thing, single replacement. 1 thing getting kicked out. A plus BC yields B plus AC, right? Where this A has kicked out this B. We additionally see this in another case where we've got A plus BC yields C plus BA, where this A has instead kicked out the C. So we see it in both cases. We've got double replacement. So if single replacement means 1 thing getting kicked out, what do you recommend double replacement would be? If you said 2 things being kicked out, you'd be absolutely correct. Double replacement, AB plus CD yields, where it's essentially this A and C switching places. Where we've got CB plus AD. Right, so 2 things getting replaced. B and D can also switch places as well, and we'd end up with the same result. The last one is the most complicated. There's no really good pattern. A combustion reaction. Here, it requires a hydrocarbon and a hydrocarbon. All that is a compound with hydrogen, carbon, and oxygen sometimes. So it sometimes has oxygen, sometimes it doesn't. And that's okay. But let's get back to the nitty gritty. Plus oxygen gas. So a hydrocarbon plus oxygen gas. This yields always, no matter what hydrocarbon you're starting with, no matter what state it's in, whether it's solid, liquid, or gas, always produces these same two products: carbon dioxide and water. So I'm hopeful that with these first four, synthesis, decomposition, double replacement, and single replacement, right, those are hopefully a little more easily identifiable as the combustion. Combustion's the problem child here. What I recommend looking for your combustion is that the products are only these two. Nothing else. That has something else in there, it's not a combustion reaction. Only those two things. All right, so with that, that ends our review. Now, there are two other possible sessions. There's one more possible session that is tomorrow morning at 6:45 a.m. in 295A. For those of you who stuck around, thanks so much for sticking around. I hope that this was helpful, and I will see you all in class. And for those of you who are visiting from MRS's class, I hope this was also informative. So please take care. For those of you watching the recording will be posted here shortly. All right, thanks so much, everybody. Have a good, safe day.